welcome to Telikilaas of the Ministry of Education, grade 4 physics. Myself, Ajita Mary, representing Center for Higher Secondary Education. Today's topic is taken from Unit 4, Further Mechanics, Momentum. Before we see the topic introduction, let us have a quick glance through the International Advanced Level Physics Specification. International Advanced Level Physics Specification has two levels, IAS level and IA2 level. IAS level is covered in grade 11, the first three units, units 1, 2 and 3. The remaining three units is going to be covered in grade 2. So in IA2 level, we have three units, unit 4, 5 and 6. Unit 4 is further mechanics, fields and particles. Unit 5, thermodynamics, radiation, oscillations and cosmology. Unit 6, practical skills in physics 2. Now let's see a brief info about Unit 4. Unit 4 is the first unit of IA2 level. It is for the mechanics, fields and particles. This unit is assessed for 1 hour 45 minutes and the maximum marks for this paper is 90. The three major topics that are covered in this unit are further mechanics, electric and magnetic fields, nuclear and particle physics. Out of this 90 marks, a minimum of 36 marks is allocated for calculation, and it's one of the scoring paper. In today's class, the major learning objectives that we are going to cover are you'll be able to understand how to use the equation impulse is equal to F delta T, which is equal to delta P in accordance with Newton's second law of motion. You'll be able to investigate law of conservation of momentum and the two types of collision, elastic and inelastic. And be able to understand how to apply conservation of momentum to problems of collisions in one dimension. Now let's begin today's topic. The first topic of Unit 4, further mechanics. Further mechanics includes momentum and circular motion. Today's class we are starting with the momentum. As you know, momentum is represented by the symbol small p, which is defined as the product of mass and velocity. P is equal to m into v, where m is mass and v is velocity. Velocity is a vector quantity, so momentum is a vector quantity. The direction of momentum is same as that of direction of velocity. As by the equation, SI unit of momentum is kilogram meter per second. So it is understood that only moving object has momentum. So if the object is stationary or at rest, its velocity is zero, so its momentum is zero. Let's see what is this change in momentum, which is represented by the symbol delta P. When a resultant force acts on an object, its velocity changes. This causes change in momentum. Change in momentum is caused by resultant forces in accordance with Newton's first law. But how to calculate change in momentum? Change in momentum is calculated as final momentum minus initial momentum. So you can make use of this formula for calculation. Delta P is equal to mv minus mu. In this, v is the final velocity and u is the initial velocity. The equation appears to be very simple, but you need to be very careful in doing the calculation of change in momentum. You need to consider the direction of velocity appropriately. For calculations, you need to use standard sign convention. In physics, the standard sign convention used is towards right is positive, left is negative, upward direction is positive, and downward is negative. Hope it's very clear now. Now let's see a situation how to calculate change in momentum. The first scenario, ball A, here the red ball of mass M, which is moving towards right with velocity v. It strikes the vertical wall and rebounds back with the same v, but in the opposite direction. You can see momentum before is equal to m into v. Momentum after is minus mv because it's moving towards left now. Change in momentum is final momentum minus initial momentum. So minus mv, it becomes minus 2mv. So look at the second situation. Here the ball B, which is moving towards right, it strikes the vertical wall and got stuck to the wall. In this case, how to calculate change in momentum? Momentum before is equal to m into v. Momentum after is 0. So change in momentum is final momentum minus initial momentum, which is equal to minus mv. So this is how you need to do the calculation of change in momentum. But this change in momentum is equal to another important quantity, impulse. What is this impulse? Impulse is product of force and time of collision. By equation, we can write impulse is equal to force into time. So the SI unit of impulse is Newton seconds, or you can even express in kilogram meter per second because it's also equal to change in momentum. Impulse momentum theorem states that when a net force is applied to an object over a certain time interval, the force will cause a change in the object's momentum. In simple terms, we can write impulse is equal to change in momentum. So with the mathematical symbols, we can express this as F into delta B is equal to delta B, which is equal to mv minus mv. This particular equation has lot of practical applications. Now let us see the significance of impulse momentum theorem. This theorem reveals some interesting relationships such as the inverse relationship between force and time. Look at the first scenario. Heavy truck of momentum mv bumps into a heap of liquid. The action is dragging on, and we can see that as the time of impact is increased, the force is decreased according to this equation. Now look at the second scenario. The same heavy truck of momentum mv bumps onto a vertical hard ball. Here the action is very fast, so time is reduced. So you can say the force of impact is increased. So there are numerous practical applications where you can make use of this impulse momentum theorem to explain the scenario. Now it is your turn to explore the practical applications where we can rightly use the impulse momentum theorem. In some cases, the force acting is not constant. In that case, the force-time graph plays an important role. When a force-time graph is given, how do we calculate impulse? Impulse is area under force-time graph. In this graph, we could see the force varies from 0 to maximum and then maximum to 0 over a time span of 0.2 seconds. How to calculate impulse? As it is said, it is area under the graph. Here it is triangle, so half base into height. You will get an answer 1 Newton second. So when a force-time graph is given, find the area under the graph that gives you impulse. Now let's see how Newton's second law is interpreted in terms of momentum. The rate of change of momentum of a body is directly proportional to the unbalanced force acting on that body and it takes place in the same direction. Meaning, resultant force is equal to rate of change of momentum. What is rate of change of momentum? It is change in momentum divided by time. By unit, we could say that kilogram meter per second divided by second, which is kilogram meter per second square. It's a very familiar SI base unit, which is nothing but Newton. Using resultant force equal to rate of change of momentum, you can easily derive the basic equation of Newton's second law. It is equal to ma. You need to know how to derive this equation. Now let's say the derivation of F equals m. For this, we are considering a simple situation. An object of mass m, which is initially moving at u, is acted on by a resultant force F. The object starts to accelerate. At time t seconds, its velocity is v. The initial momentum of this ball is m into u. The final momentum is m into v. So the change in momentum is mv minus mv. Since the time taken is t, the rate of change of momentum can be written as change in momentum divided by time. So mv minus mu divided by t. In this, v minus u by t is acceleration. So by following this simple sequence of steps, we will be able to show that f is equal to mu. Hope you understood this derivation. Now let's move on to the next section, that is collision. So what is collision? Collision is interaction between objects in which momentum is conserved. Momentum is conserved. Let's see how momentum is conserved in collision. By applying Newton's laws of motion, we can prove that momentum is conserved in collision. So far we have seen change in momentum is caused by resultant force, that is in accordance with Newton's first law. The rate of change of momentum is equal to the resultant forces, Newton's second law. Now the conservation of momentum is by Newton's third law. Investigation of conservation of momentum by Newton's laws of motion. In this situation, you can see there are two balls which are initially moving at u1, u2 respectively. They collide with each other, and after collision, they move off at two different velocities, v1 and v2 respectively. So what happens when they collide with each other? When they collide with each other, the red ball exerts a force on blue ball, and blue ball also exerts a force on red ball. By Newton's third law, the famous Newton's third law states that to every action there is an equal and opposite reaction. More elaborately, we can say that if a body A exerts a force on body B also exerts an equal and opposite force on body A. They are equal in magnitude but opposite in direction. So F1 is equal to minus F2. Now we write the force in terms of rate of change of momentum expression. We get this step. In this equation, delta P is cancels off as it is common on both sides. And rearranging these terms, you will end up with the equation m1u1 plus m2u2 is equal to m1v1 plus m2v2. So what does the left-hand side indicate here? m1u1 plus m2u2 is the total momentum before collision. What about m1v1 plus m2v2? It is the total momentum after collision. So momentum is conserved. Total momentum of a system before collision is equal to total momentum after collision, provided no external forces are acting on the system. And this is what we call the law of conservation of momentum. So in law of conservation of momentum, the important condition is no external force acts on the system. Momentum is perfectly conserved in all collisions. So when you get problems of collisions, we can directly apply the law of conservation of momentum in order to solve them. So in this practical situation, you could see a heavy truck bumps onto a moving car. After impact, they are moving off with two different velocities. So here almost all the data are given except the final velocity of the car after impact. How do we find the final velocity of the car after impact? So when you apply law of conservation of momentum for this impact, m1v1 plus m2u2, that's the total momentum before collision, is equal to m1v1 plus m2v2, just the total momentum after collision. You will be able to find out the velocity of the car after impact. Here m1 is the mass of the first object, m2 is the mass of the second object, u1 initial velocity of the first object, u2 initial velocity of the second object. v1 is the final velocity of the first object and v2 is the final velocity of the second object. So by substituting all this data, you will be able to find the unknown quantity. Now let's see the types of collision. All the collisions are broadly categorized as elastic collision and inelastic collisions. What is an elastic collision? An elastic collision is collision in which kinetic energy is conserved. What is this kinetic energy is conserved? That is, kinetic energy before collision is equal to kinetic energy after collision. But this type of collision is very rare in practice. But still you can quote examples as Newton's cradle, pool ball collisions, which are considered as nearly perfectly elastic. There's a very little loss of kinetic energy that can be neglected. Now let's see what is an inelastic collision. An inelastic collision is collision in which kinetic energy is not conserved, meaning kinetic energy before collision is not equal to kinetic energy after collision. Almost all the practical collisions come under this category. Example crashes, collision between vehicles, etc. Now let's see one example from elastic collision and one example from inelastic collision. So as I said, Newton's cradle is nearly perfectly elastic. Newton's cradle maintains kinetic energy as well as momentum in its collisions. It's a desktop toy. Here, all the balls are identical in all respects. So what happens if I displace one ball from one end? Let's see. When one ball is displaced and released, you see on the other end, one ball is ejected out. So momentum is perfectly conserved. So what happens if two balls are displaced from this end? So definitely two balls will be ejected out on the other side. It's a very interesting actually desktop toy which clearly shows momentum is conserved. Now let's see an inelastic collision example. A collision where the bodies join together. If two balls of modeling clay collide with each other, they stick together as shown in figure. We want to find the velocity of the combined lump after the collision. So here you can see the red ball moving at 6 meters per second bumps onto the blue ball. Both are moving up together with a common velocity after impact. So how do we find out this final common velocity? As I said, we can directly apply momentum conservation. Momentum before is equal to momentum after. Substituting all the known data, you'll be able to find out the final common velocity. So this is example of inelastic collision. So there is a loss of kinetic energy. What exactly happens to that kinetic energy loss? It is usually converted as heat and sound energy. In other words, according to law of conservation of energy, the work done sparing the balls is equal to the loss in kinetic energy. So how do we find this loss in kinetic energy? Kinetic energy losses kinetic energy before minus kinetic energy after. So using the known equation half mv square, you'll be able to find out the kinetic energy loss. The final answer has to be expressed with appropriate units. Now we are almost towards the end of today's session. Before winding up, let us see some past paper questions from the topic that we have covered so far. Question number 1. Which of the following is a possible unit for rate of change of momentum? So it's rate of change of momentum. So it is understood that the unit is kilogram meter per second square. So the correct answer is C. The second question. At an airport, suitcases of mass 22 kg are placed onto a conveyor belt moving at a speed of 0.75 meter per second. 12 cases are placed onto the belt every minute. Which of the following gives the average horizontal force exerted by the belt in newtons? So here it is force. As you know, force is rate of change of momentum. Change in momentum divided by time. Time is 1 minute, which is 60 seconds. So the correct option here is C. And the last question here. Select the row of table that correctly identifies what happens in an elastic collision. You know, elastic collision, kinetic energy is conserved. So if you look at all these options, the correct answer is A, where momentum is conserved, total energy is conserved, and kinetic energy is conserved. Now let us see a quick summary of what you learned today. The impulse momentum theorem. Impulse is equal to change in momentum. We have learned that Newton's second law in terms of momentum, law of conservation of momentum, the types of collisions, both elastic and inelastic, and you know how to use conservation of momentum in problems of collisions in one dimension. and we could see the practical applications of conservation of momentum and kinetic energy. Hope you got benefited from today's class. The remaining half of this topic is continued in the next Telikilaas. Until then, bye. Thank you. Wish you all the best.